Hey guys, welcome to our lesson for section 2.3, exponential functions. So this is just going to be a really basic intro to exponential functions. We'll do some examples, we'll talk about their properties and stuff like that. In the next section we'll get into kind of working with them and finding their equations and such. So the first thing we want to do is we want to define what an exponential function is. And very simply, we can say that an exponential function is any function that can be written as f of x equals a times b to the x. Now there's some conditions on this, but first I want to talk about what's happening here. So an exponential function is all multiplication with our independent variable being the exponent. Okay, so that's kind of the big difference. There's something called a power function where we have something like x to the something, whatever number that may be. And that's a little different because then x isn't the exponent. Here, the independent variable, our input, is the exponent. So let's talk about our conditions. So the first condition is simply that a does not equal 0. And if we think about why that is, it's very simple. If a is equal to 0, well, 0 times anything is 0. And so we just end up with a constant function 0, and that's not really an exponential. Exponentials have some change and stuff like that going on, and so a cannot be 0. We have another condition that b cannot equal 1. And for a very similar reason. If b is 1, 1 to any power is always 1, so we get a times 1, and that's just a. So again, we get a constant function of a. So in this case, we'd get a constant function of 0. In this case, we get a constant function of a. There's one more condition, and this kind of has two things wrapped up in it. B has to be greater than 0. The reason for this is very simple. If B is 0, we get kind of a similar situation here. 0 times 0 to any power is 0 times a is 0, we get 0. But what happens if b is negative, right? That's kind of the weird-ish spot. And it comes really down simply to what we talked about in section 2.2, is let's just say we have a simple function, g of x equals negative 2 to the x. Mind you, this is a function. It's just not an exponential function, okay? Because what it meant for something to be a function was there's a relation where for every input, there's exactly one output. Well, if I put something in for x, I'm only going to get one thing out. Okay, but what happens at g of 1/2? Well, that's just negative 2 to the 1/2. Well, we talked about that in section 2.2, right? Rational exponents, that's just the square root of negative 2. This is a non-real number. So we don't want that. And even further so, if we just looked at integer values for x in this one, let's just say we had an even simpler function, h of x equals negative 1. Well then when x is 1, we get negative 1. When x is 2, we get positive 1, because negative 1 squared is 1. When x is 3, we get negative 1. So what ends up happening at the integers is it just bounces back and forth. And so these two things give us a lot of issues. And so what we do is we restrict the base of our exponent, of our exponential piece, has to be greater than 0. Not greater than or equal to, but greater than. Okay? So this is our definition of an exponential function. And what's really cool is exponential functions are extremely similar to linear functions. Let's talk about how that is. So if we have good old f of x equals a times b to the x, so this is some exponential function, okay? And then we've got our linear function, good old mx plus b. These b's are totally non-related, anything like that. There's no restrictions for this, which is nice, but there are restrictions for this, which we talked about. And those reasons are just to avoid having a constant function or to have a wibbly-wobbly craziness. So let's talk about how these are similar. Okay, first of all, how does this change? We know m is our slope, right? And that's our rate of change. But let's think very specifically. If the input goes up by 1, what happens to the outputs of this function? Well, if you think about it, right, it's rise over run, right? So if our slope is 5, we go up 5 over 1. So if our input goes over 1, that means we went up 5. So this, what happens? So if x goes up by 1, we add m. What happens over here? If x goes up by 1, so let's just say, for example, x is 2. So we have a times b squared. If x goes up by 1, that means we have a times b cubed. So let's write that. A times b squared, a times b cubed. Now, I can't really necessarily see the difference, but let's expand those based on our basic definition of exponentials, of an exponent. So this is a times b, and this is a times b times b times b. Right? B squared means b times b cubed is b times b times b. Look at, what's this right here? Well, that is just a times b squared, which is that right there. So what happened? So when I took my x up 1, what happened? I took my previous output, this whole thing, and I multiplied by b. So here, if x goes up by 1, we multiply by b. What's really cool is both of these functions, if we look at an equation, an exponential and or a linear, we can tell the rate at which it changes just by looking at the equation. Now, the way we talk about the rate of change is different. Here we talk about it as a slope, and we'll talk a little bit later about what we talk about here, and we'll talk about its rates of change and so forth. But the difference is a linear function is changed additively, whereas an exponential function is changed multiplicatively. So that's really the main difference between these two functions. One represents multiplicative growth, one represents additive growth. Okay? Now, we know that m is from just looking at this equation, but what else do we know about this function g of x? Just by looking at it, not doing anything else. Just I look at this equation, I go, I know two things. I know the rate at which it changes, its slope, and I know its y-intercept, right? So we know based on this that g of x has a y-intercept of at point 0, comma, b. And we can very easily show this because this is x comma y, right? So input, output. So if x is 0, we get 0 times m is 0. 0 plus b is b. What's our y-intercept here? Well, so to figure out a y-intercept in general, for any problem ever, we just make the input 0. That's all we have to do. So if our input is 0, so we get 0 here. So we have b to the 0. What is b to the 0? What's anything to the 0? That's right, it's 1. And 1 times a is just a. So this, so we know that f of x has a y-intercept at 0, comma, a. So what's really cool is both of these functions are very similar. Additive growth, multiplicative growth. Both of them, we can just look at their equations and we know at what rate they grow and where their y-intercept is. And we can also do some other cool things. So what else does the slope tell us? Let's think to linear functions. What does the slope tell us? Other than its rate of change, but more specifically, we can kind of classify its rate of change into two different groups. It's either increasing or decreasing, right? And we can simply say, okay, if m is greater than 0, that means this is increasing. If m is less than 0, you're decreasing. Now, if m equals 0, we have a constant function, right? And that's not something that's not a relation we get between the two, and that's okay. Not everything, they're not exactly the same. But just the same way that we could tell whether this function was increasing or decreasing by the m, the rate of change, we can use the b value here to tell whether it's increasing or decreasing. Now, if you remember, our restrictions on b were that it had to be greater than 0 and not 1. So in other words, it's a positive number, not 1. Okay? And that gives us a natural little split. It gives us everything between 0 and 1 and everything bigger than 1. And so we get two situations. We get that 0 is less than b is less than 1. And we get that b is greater than 1. Okay? What do these two cases give us? Well, if we think about it, right? Every time x goes up by 1, so as we increase along the x-axis, we're multiplying by b. So if I multiply something by a number that's smaller than 1, that's between 0 and 1, so like 0.5, 0.25, 0.1, 0.9, things like that, our numbers are going to get smaller. So if we have this, our function is decreasing. And the way we talk about decreasing with an exponential function is we say that we have exponential decay. And so that is what we talk about. So if b is less than 1, we say that we have exponential decay. And what if b is bigger than 1? Well, remember, as x goes up, we multiply by b. So every time x goes up, I multiply by something bigger than 1, which means my number gets bigger and bigger and bigger. So this is increasing. But with an exponential function, we call that exponential growth. And that's it. Pretty easy, right? So there's some really nice analogies between these two guys. Okay, we can really easily kind of make some of those connections between a linear function and an exponential function. And we're going to see those further on as we do some more things, as we look into section 2.4, where we're going to be finding these equations. One of the ways we're going to do it is given 2 points, which is something we did with this all the time. And we're going to talk about kind of how we do that. It's a very similar process. We figure out if we know one of the things, we plug things in, we use some formulas, and it's pretty easy. So let's stop comparing these two now. I want to actually continue talking about these exponential functions because that's what we're all here about. So I want to talk more about this and kind of this piece here. When we talk about a linear function growing, we say like, oh, it has a slope of 5. Okay? But when we talk about exponential functions growing, we talk about it either having a growth or decay rate, the rate at which it's growing or decaying. And there's two equations for that, depending on whether we're talking about exponential decay and exponential growth. And it's really easy to mix them up, but it's really easy to figure out if you mixed them up, and then it's really easy to fix it. Okay? So if 0 is less than b is less than 1, then the decay rate can be found by a very simple equation. Okay? 1 minus b. That's it. 1 minus b. And so that's all we have to do to figure out the decay rate. So if b is between 0 and 1, we just do 1 minus that b value, and that gives us our decay rate. Now, similarly, if b is greater than 1, then the growth rate can be found by b minus 1. So now you see how those are really easy to mix up. But let's do some examples real quick. So if b equals 0.83, okay? So first of all, do we have exponential growth or exponential decay? Right, we have exponential decay, because that's between 0 and 1. So the formula we should use is 1 minus b. But what happens if we use the wrong formula? Okay, that's easy. So if I have 0.83 minus 1, that's negative 0.17. Your growth or decay rate should never be negative. And so if you end up with a negative, you go, oh, I mixed my formula up. And then you just go, okay, so it should actually be 1 minus 0.83. And lo and behold, that's just 0.17. And so if you ever get a negative number for your growth or decay rate, just go, oh, I did the wrong formula, and then just remove your negative, and now you have your decay rate. So some people I know have kind of simplified this process for themselves. They just go, I'm always going to do b minus 1, and then just whatever it is, make it positive. It's not wrong, but it's not fully right either, if you understand what I mean. On the test or anything like that, it's going to get you to the right place, but it just kind of adds an extra step. So now let's talk about what these decay rates and growth rates mean. And the easiest way to do that is with a word problem. But before we get there, let's talk about the graphs of these. So the graph of an exponential function is really interesting. We've all probably seen them before at some point in time, whether we knew it or not, but let's look at a very specific example, and we'll just say f of x equals, let's go 3 times 2 to the x. So first, is this growth or decay? Is this exponential growth or is this exponential decay? That's right, it's exponential growth, because our b value is 2, which is greater than 1, so that's exponential growth. So from here, I know that this is exponential growth. Where's my y-intercept? A good old internet @ symbol. Right, our y-intercept is at 0, 3. Perfect. So I want to look at this, and I want to see what happens at this function kind of as x goes around. So I want to create a table. And so I'm going to have a very simple table of x, f of x, right? Not x, y, because we're talking about function notation here, right? So we want to keep that on. So I just want to do very simply, let's go -2, -1, 0, 1, 2, and 3. So we already know 1 point. We know it's 0, 3, so we can fill that in 0, 3. Now, let's start with the simple ones. Let's go positive. So if x is 1, we get 3 times 2 to the first power. So the first thing we need to do with the exponent, 2 to the first power is 2. Awesome. 2 times 3 is 6. Now, f of 2 is going to be 3 times 2 squared. 2 squared is 4. 4 times 3 is 12. One more time. 3 times 2 cubed. 2 cubed is 8. 3 times 8 is 24. Now, I want you to notice something here. Okay? Remember when we talked about when these are linear functions and stuff like that, right? A whole few minutes ago. We said that we could, if x goes up by 1, we multiply by b. Our b here is 2. So if x goes up by 1, we should be multiplying by 2. And let's see if that happened. Go from 0 to 1, 1 to 2, 2 to 3. So those all go up by 1. So start at 3. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. Awesome. So for -1 and -2, one thing we could do, plug these into the equation if you know how to deal with that mentally, right? 2 to the negative first power times 3, work with that. You can always use your calculator. But let's also think about this. If going up multiplies by 2, what happens to, how do I go down? Well, to get from 24 to 12, we divide by 2. Divide by 2, we get 6. Divide by 2, we get 3. So to go to -1, I get 3 halves. Write that little room savery. And then I divide by 2 again. For x equals -2, and I get 3/4. If I do that again, I would get 3/8, 3/16, 3/32. And you see the numbers getting really, really small. But is it ever going to go to 0? Will it ever equal 0? Let's try. Let's use our calculator, because we're going to get some really big negative numbers. Let's see. Let's find, what is f of -1 million? What does that equal? Well, it means I need to do 3 times 2 to the -1 million. It's 1 followed by 6 zeros. So if we use our calculator, so 3 times 2 raised to the negative. And we can just type it in exactly like that. We don't have to do this piece. We don't have to do 2 to the negative 1 millionth times 3. We can do it all at once. And it's actually better to do it all at once. And remember, if your calculator doesn't do this little kind of jump up into the box thing, you're actually fine here. You don't need parentheses around that, but it's always a good idea to do that just to practice so you never mess it up. Notice I always put this 2 in parentheses. Again, that's just a practice thing to keep it habit, because if we don't, we might accidentally type in our calculator 32 to the negative 1 millionth. That's not what we want. So I do that, and my calculator says 0. Is that true? Does that equal 0? When our calculator says so, it can't be wrong, right? Wrong. It's not 0. This number does not equal 0. It is so extremely tiny that it's so imperceptible. It'd probably, if you use scientific notation, would be the only way to write this. And it would have to be something like times 10 to the negative 1 millionth or so. And the reason why our calculator says 0 here is our calculators are a type of computer, and computers have memory. In other words, they have so many things they can kind of hold on to in their head or in their computer before they start to cut things off. And so our calculator, I don't know exactly, I believe it's about 99. So our calculator, imagine, it can hold 99 spots in one number. So it can hold a 99-digit long number. And anything beyond that, it just cuts off and rounds that number. So if a number is 0.00000 and it has 99 zeros, our calculator cuts everything else off, and so it just sees 0 point and all zeros. So your calculator goes, oh, this number must be 0. But it's not. And the reason why is very simple. If I multiply two numbers together, avoid A and B, that's what we're using for this. Let's say we multiply C times D, and that equals 0. How is that possible? How can I multiply two numbers together and get 0? There's only one way. And that way is for at least one of these guys to equal 0. So if the product of something is equal to 0, one of these two things has to be 0 itself. Okay? So let's think about this. Is 3 0? No. Is 2 0? No. If I multiply 2 by itself, negative 1 millionth, that's kind of weird, right? Remember, this is just 1 over 2 to the 1 millionth. So if I multiply 2 by itself a million times, still just multiplying a bunch of 2's. None of those are zeros. So none of these are zeros, which means that product cannot equal 0. So an exponential function, unless you add or subtract something on the end, so if I did something like this, minus 2, okay, that would pull it down and that would equal 0. But doesn't happen. Or it didn't happen, but we're not going to deal with that. We're going to deal with these. So this will never equal 0, which is really cool. So let's look at this graph. Let's try and graph this. Okay. So since it never equals 0, and never goes negative as well, for a similar reason. So we have a positive 3 times a positive 2 a bunch of times, so that's never going to become negative. We can kind of focus on just the positive 2y quadrants. So negative 1, negative 2. So I know this goes through at 0, 3. So this is 12. So we go through at 0, 3. And then we have a point 1, 6, 2, 12. And then 3 is up here on my wall. I'm not writing my wall. My wife will get very upset. The next is 3 divided by 2. What is 3 divided by 2? It's 1.5. So at negative 1, you get 1.5. Then 3 divided by 4 is 0.75. So that's about here. So if I just connect these, and now this is going to be slightly curved, okay, it does that. Now what happens over here? Well, as I go out, it keeps getting smaller. So 3/8 is a little bit smaller. And what this actually does is it comes and kind of flattens out along our x-axis. And this is something that we call an asymptote. An asymptote, in this case, this is a horizontal one because it's a horizontal line, is just a line that our graph gets closer and closer to but never touches. That's a term you may hear. It's not one that I'm going to do a whole lot with in this class. You'll definitely hear it in Math 111, so if you move on to that, you'll hear it a lot. So this is what a basic exponential graph looks like. And this is exponential growth. So notice it is growing as x increases. Now, I'm going to erase this. And so I'll just kind of do a little sketch. So exponential growth in general looks something like this. Whereas exponential decay is the opposite. As we go, it decreases. And so this right here is exponential growth, which means b is greater than 1. And this right here is exponential decay, which means 0 is less than b is less than 1. Now, there's one thing for both of these. For both of these, a is greater than 0. Now, that's not a requirement of our function. A can be negative, that's fine. What that would just do is it would just kind of flip our functions over. And so if a was negative, it would kind of look like that. And if here a was negative, it would look like this. And so it kind of messes things up. So when we're talking about exponential growth and decay, we're mostly talking about in applications and things like that. We can talk about any function, any exponential function, but when we're really dealing with it and working with it, it's in an application, in which case a is usually not 0, or a is usually not negative. Okay. All right. So there's a graph and function. Now let's talk about a model. Let's talk about a situation and kind of talk about how we can use these ideas. Actually, let me make sure that works. Might be jumping the gun on you. Okay, you know what? Jumps the gun on you guys. This is it for this lesson. So, that's it for 2.3. I'll see you guys later for 2.4.